Yeah, so with that, is there a question in something that's not clear in the notebook or in the exercises? Well, fantastic. So if I don't see anything, then we have a lot of time today, because then I think we should be finishing this session, because all I really want to do in this session is to basically clear up any uncertainties that you have after reviewing the lecture notes and the video guide, doing the exercises. But if there are no questions, fantastic. Then the next session will be on Wednesday, and we're going to do sort of similar what we did here for the Gaussian. We're going to do it now for discrete variables, and we're going to introduce the binomial distribution and the categorical distribution. And it's going to be a sort of a similar class, but now on variables that I defined on a discrete alphabet. After we've done that, basically we can take off and start working on real applications, regression and classification, and even beyond that. So all the, let's say, all the difficult part is sort of behind us now. From here on, let's say after next lesson, the next lesson, we're going to go more and more towards the applications. So last chance to enter a question, and otherwise I'm going to wish you a great weekend.
Bert,
Yeah.
yeah, I was going to add to this. Like, we also didn't get any Piazza questions on this particular lecture this week. So maybe we can just check with the students whether all of this was clear. Can everyone, yeah, if this week's material or this session's material was clear to you, could you post something in chat?
Think the material should be clear. It's not really difficult, although I would agree that some of the computations are a bit, you have to really watch out. Let's say here's a computation. What goes in here? Let's say this is and you see this a lot, a Gaussian of x and x given theta, and then a Gaussian of theta given mu n. So what we do is we can exchange xn plus 1 with phi here, with theta. It will still be the same Gaussian. And then you can use the multiplication rule of the Gaussian. And to get some normalization factor times an integral of basically a Gaussian over theta, that integral will go to 1, and what's left over is just a normalization factor. It's this rule here. Let's see, this rule here that you'll use. But this rule is very useful for nearly all of these when you have to work something out, like here as well, when we go to here, for instance, right? We always use this multiplication rule to work this out here. Once you get the hang of that, then I think you can do these exercises and you can actually come up with analytical answers like a Kalman filter. But that's sort of a computational thing that you have to see once. I do not understand how to get to the last part of that computation. So the computation that I just showed is going to be the same one as I do here. So here I'm going to do it again. I'm going to assume that you know Bayes rule, so that we we don't get to Gaussian times a Gaussian. Now, if we look at the multiplication rule, yeah, I'm going to have to switch back and forth now. Sorry about that. But if you look at this multiplication rule, let's see. Yeah, so it says if I multiply a Gaussian over x with another Gaussian over x, I'm going to get here a Gaussian over x times, yeah, something that is not a function of x. So this is with respect to x, just a constant. It just so happens to be that this constant can be expressed as a Gaussian, but don't be mistaken. This is a Gaussian in mu a, but it is just a number. So this is just a number times a Gaussian, right? And you can also, I mean, very often, let's say if this would be a prior and this would be a likelihood, then this would be the posterior and this is the evidence, and the evidence is, yeah, it's just a number. So a Gaussian times a Gaussian, if they're both in x, gives a Gaussian in x and some number. And now we go back here. So I have here Gaussian over x times a Gaussian over, hey, theta. So I can't multiply the two. But this one, the first one, yeah, xt and theta I can exchange, right? Because if you look at the Gaussian expression, you'll see that if you exchange theta and xt, it's the same Gaussian expression. And now I see, okay, this is a Gaussian over theta times a Gaussian over theta. Okay, but then we can do, we can use this Gaussian multiplication formula, right? That is going to be that is a function of theta. This equality here should be a proportional to. And the mu t and sigma t squared, yeah, they are functions of xt, theta, or sigma squared, mu t minus 1, and sigma t minus 1 squared. They're function of the parameters of these two Gaussians. And that you can just see again if you go back to here, right? Mu c and sigma c are functions of the parameters of these two Gaussians, right? Of sigma a, sigma b, and so forth. And so that you just fill in, and then you are set. Right, then it's a question. I mean, then you have this expression, and then it's just a matter of, yeah, working, sort of rearranging it so that this Kalman gain appears. And we've done that a few times. I'm not sure if we've done it explicitly here, but I think we've done it a few times in the previous class when I try to, yeah, when I do it here as well. It's just rewriting this as a prior plus some gain times a prediction error. It's just a sort of a rewriting. You do that a few times, and then you can rewrite it in this form. So there are two. Let's say this is sort of a derivation that's good to be aware of. There's a trick here of exchanging theta with x, and then you have to use this multiplication formula, and then you can get to this if you rewrite it. So it's quite a few things, but it would be good to work through that. I think there's also an exercise when you go through this. This is the most difficult thing really of this class in terms of computation. But if you can do this, then basically you can derive the Kalman filter, manually, and that's nice. I see that one person says I'm lagging one lecture behind. Of course, that's fine. So feel free to post questions in Piazza about this lecture, even though we may be, in the next lecture. So I mean, that's totally fine. I'll be happy to keep answering questions in Piazza about any of the previous lectures. There's one tricky thing that I will also emphasize, and that is that it's important to see the difference between multiplying two Gaussian distributions and multiplying two variables that for where each variable has a Gaussian distribution. Unfortunately, now in the NB viewer graph, it's not rendered properly, but it is rendered properly here. If you multiply two Gaussian distributions, you get a new Gaussian distribution. It's very useful for Bayesian inference when you multiply a prior with a likelihood and they are both Gaussian. So, but it's a different thing to say, oh, I have here a z, a new variable, which is x times y, and x has a Gaussian distribution and y has a Gaussian distribution. That doesn't mean I can multiply the distributions. Right, it's actually I have to do quite of a difficult computation. It turns out I get a very different problem z. Here is in orange are two Gaussian distributions, px and py, and they're both simple Gaussian distributions. If I multiply these two distributions, a Gaussian times a Gaussian, I get a new Gaussian. Sorry, this one. And that means that the orange one is also a Gaussian. However, the distribution for z, and z is here the product of these two variables, so not the product of the distributions. Yeah, that's a Bessel function. That's a different thing. So that's good to keep in mind and think about that a bit. Those are, from my viewpoint, let's say, to keep this in mind well and to do this computation are the sticky points. Let's say, yeah. And aside from that, I think you should be able to, yeah, to just work your way through this class. Are there any other questions? Okay, so I think that adding, yeah, I tried that. I tried that. It doesn't work. The question is, you should add here. Flush cache is true. Flush cache equals true. Boom. Oh, sorry. That's what I need to do here. So I'm going to add flush cache equals true. I'm such a bad cache equals true. Yeah, capital for true. Okay. Boom. Okay, so now let's watch at the bottom. Unfortunately, it didn't work. So I think there was a bug in NB Viewer. NB Viewer is okay, worked in your browser. That's fantastic. So it may just be a thing of NB Viewer together with Chrome on a Mac. Yeah, a private tab. Okay, I'm going to try that. I'm going to try that later. Okay. And if it works, I'll let you know. But it's not a really big thing, but I would like to solve it. So, are there any other questions with respect to the class? Those, then that's totally fine. It's just on my end. So I will work on it. Okay, so I then will wish you a happy weekend. Let me know in Piazza if you start really falling behind, because then we should come up with a way to let you catch up. Because that's I don't want to have all these let's say these meetings with, let's say, and half the class is totally behind, and we need to maybe throw out a lecture, or we need to think about how you can catch up. Okay, so maybe we should do a poll in let's do a poll. I will do a poll in Chrome or in Piazza just to check how things are going. Okay. Then I think I'm going to finish the lecture or the class. And for so many times now, I wish you a nice weekend. Okay. Bye-bye then.